Hello students, we're continuing with chapter 4 and we're talking about acids and bases. So this is definitely a section to really focus on because it's foundational. When you move on to Chem 160, you're going to use a lot of these same acid-base principles, and also in organic chemistry if you take that course as well. So just in general terms, you guys have some familiarity with acids. They can taste sour. They can react with certain metals to produce H2. For our purposes, the most important is they react with the base to form water and a salt. Bases are bitter. They do feel slippery. I felt those. Generally, you want to wear gloves, and even with gloves, I can experience that. And they react with an acid to form water and a salt. So acids are very special substances. The reason is they start out covalently bonded, which we know have no ions, electrons are shared. But when acids are dissolved in water, such as HCl, they can produce ions. This is a very, very special category. All other covalent compounds, they're not made of ions. Electrons are shared, and when you dissolve them in water, they stay intact. This actually generates an H+, which we call a proton, because a hydrogen atom that lost an electron only has a proton. And you get the other anion out of that, Cl-. So you can see here, HCl, that'll give you H+ and Cl-. Sodium hydroxide, which is a base, will produce hydroxide ions in solution. So sodium hydroxide is typically a solid. That will be an array of alternating cations and anions. So it's more of an array, not just this individual guy here. But basically you get Na+ and hydroxide. What's important for acid-base reaction is when you have an acid, the H+, and a base, the hydroxide minus, these will find each other and form water. And they're reactive, they're charged. You may be familiar with pH. pH is just a measure of acid strength, and it uses the logarithmic scale, which is powers of 10. So the lower the pH, the more acidic. The higher the pH, the more basic or alkaline. So here are some common household substances. Coffee is a little bit acidic, and you will likely, you are actually going to do some problems in class using pH. So the way that you use that is, say you know the concentration of the H+, you can just take the negative log of that using your calculator, and that'll give the pH. So you could put the number in, press log, and then take the negative of that. There are times when you actually measure the pH. So it's possible you may do a lab where you're actually using a pH probe of different solutions, and you're measuring the pH, and you actually want to know and calculate the H+ concentration. In that case, it's the anti-log. So you say the pH is 5. You would take 10 to the minus 5, and that would be your concentration of H+. I wanted to take this opportunity to talk about ocean acidification because it's relevant to what we study. I have a picture on the next slide, but basically there's an increase in global CO2 production. This is just because of the burning of fossil fuels. And the problem with that is that more of it is at the ocean surface, and carbon dioxide naturally moves between the air and the ocean, but with a huge increase of carbon dioxide, that increases the amount that'll go and dissolve into the ocean. Under normal circumstances, marine plants, phytoplankton, they naturally use the CO2. However, one problem is some of that CO2 in water is converted to an acid, carbonic acid. So normal situation, you get some carbonic acid. Just to let you know, marine animals, they use carbonate to build their shells. But if there's H+ from carbonic acid, that H+ is going to react with carbonate and basically take it away from the marine animals that need it. We go from the late 1800s where you have a pH of over 8 to a pH of under 8 projected for 2100, the year 2100. So with more CO2, more carbonic acid, more H plus to sequester or use up the carbonate. And so you get fewer, smaller marine calcifiers. What does that look like? The shells start dissolving is one. And that's the biggest thing. They need carbonate to build their shells. So eventually, if the ocean is too acidic, coral can dissolve, affecting those ecosystems. Okay, back to our regularly scheduled program. Acid-base reaction, I mentioned H plus and hydroxide form water as a product. This is our classic. If you have equal amounts here, or basically just one H plus and one OH minus, they neutralize each other to give water. The reason why we say neutralize is because they start out one each is charged and then you get a neutral water. The driving force for this is you're forming this neutral covalently bonded water molecule. And this is one time where you'll see the state of matter as a liquid. The other thing I want to mention is I say H plus, that an acid gives up H plus in water. But the reality is that H plus is bonded to a water molecule itself. So H plus connected to water, H2O, is actually H3O plus. So it's a water molecule. So here's a water, an O and two H's, but with an extra H plus. So I just mentioned that because for simplicity, we use H plus, but sometimes you'll see it as the hydronium ion. Why does this happen? Go back to the reason I said an H plus is called a proton. Without its electron, it's just this ball of positive charge. So it's begging for something negatively charged, and the lone pairs of water, it's all surrounded by water. So the lone pairs of water will connect with that H plus to give H3O plus. This is just to familiarize you guys with strong and weak acids. HCl, HBr, nitric acid, sulfuric acid, these are probably familiar to you. And also weak acids, the most famous weak acid you'll use is acetic acid. You've already seen that. And the big difference is strong acids completely give up their H pluses. Weak acids are mostly intact and only give up a little bit. Almost all bases are strong as hydroxides here. So all hydroxides are strong, meaning they'll dissolve and give up that hydroxide. The only weak one is ammonia, NH3. And if you notice, there is no hydroxide. There are other definitions of bases, and I'll explain why this is considered a base. So I'd like to go through a couple examples of strong acid reacting with strong base and then looking at a weak acid. My example is HCl and barium hydroxide. Something very important to pay attention to is barium's a 2+ cation, so it needs 2 hydroxides. That means if I have 2 hydroxides around, how many H pluses do I need to completely react with it? 2. That's why I have 2 HCl's. So think about that when you're doing these reactions. This is similar to, you can kind of solve this problem and predict the products by doing the inside-outside method, or making sure you balance the equation, or just realizing, okay, 2 hydroxides and 1 H plus. We'll need 2 in front here. And then you get barium chloride as well as 2 waters. So just think about this. I would draw a picture of all the ions in solution for the reactants and then the products. You'll see that if you have 2 H pluses, 2 OH minuses, you shouldn't have any of those ions left, just the spectator ions, and then the intact water. So here I show it in the total ionic form. 2 H pluses, 2 OH minuses give you 2 waters. That's your net ionic equation, simplified. The next is a weak acid, such as acetic acid, and a strong base, such as sodium hydroxide. Here I only have one hydroxide, and I have one H+, so that'll give me sodium acetate, aqueous, and water. Draw a picture for this one, and remember that I said acids only dissociate very, very little. So only a little bit is in the H+ and acetate form, but most of it is intact. 99% actually exists as the acetic acid fully covalently bonded compound, and only 1% is H+ and acetate. That's the reason why we can use acetic acid in vinegar. That's what is in your salad dressing, vinegar, which is dilute acetic acid. Just to let you know, even though a little bit produces H+, if you ever wanted to completely neutralize the acid, you still look at how much acid you have, and you would need the same moles of base. So I'd like to show you this picture here of strong acids versus weak acids. Hopefully your picture kind of looked like this. Strong acids, let's say it started out like this, like HCl, will be 100% separated into ions. Weak acids, starting out here, is still mostly intact as the covalently bound form and only a few ions in solution. The last type of acid-base reaction is a gas-forming one, producing CO2. You'll see this come up quite a bit in some of the problems and in your lab. Basically, this doesn't have a hydroxide, but this carbonate can react with two H+, so carbonate's a 2-, so it'll need two H+, to give an intermediate H2CO3. But this, so if you did the inside-outside method, you would have come up with this. But this is very unstable. This is carbonic acid. This will decompose into water. Look here, H2 and one of these O's, and what's left over? CO2, carbon dioxide. So this is a useful reaction. You see bubbling. Sometimes you'll see this used in antacids to sop up HCl in the stomach, say using calcium carbonate, and you see bubbling with that. And another thing is if you do any baking without eggs, sodium bicarbonate, which is baking soda, and vinegar, the acid, those will mix to form CO2 gas bubbles that will help make your muffins or other baked goods rise. And the last slide for this section is talking about a different type of acid and base combination. And this explains why ammonia is considered a base. In this Bronsted-Lowry definition, an acid is just something that gives up a proton. A base is a guy that accepts it. So say an acid gives up an H+, this N that has a lone pair here, a lone pair is just two electrons that aren't bonded to anything, it'll want to grab on to the H+, just like what we saw when water grabbed the H+ to form the hydronium ion. And in this case, you form ammonium cation, which you've already seen. All right, you guys, I'm going to end here, and we'll continue with chapter 4 next time.